Good afternoon. My name is Shang. I'm come from Weiwei University as technology. Today, I have a great honor to have the organizer given the opportunity to share our work. Today, my topic of the title is Numerical Study on Spray and Combustion Process based on Eulerian spray model and unsteady-flamelet progress variable combustion model. First of all, this is the outline of my report. It contains an introduction, which includes the background and the objective. And there is the methodology, is contains the modeling approach and computational model setup and the determination of combustion metrics based on the simulation. And then we will talk about the study on this purpose, the sigma and unit model on the two different fields. One is the auditing, and another is the PF, and last is the summary. Okay, as we know, IC is the main core source in the transport section. We deal with high thermal efficiency and high power output to reach volume ratio. But due to the environmental exclusion of green cost, the engine has some issues, like for example, fuel is not renewable and high smoke emissions and high noxious emissions. So we have to demand for clean or efficient combustion facility. One is the importing new combustion model like RCCI or GCI, and another we have to find the new fuels. But we need to understand the different fuel properties on combustion process. As we know, the engine is so complex, diverse. So if we improve the very small change, we need to give the great effect. So, but unfortunately, we have the very useful tool is the numerical simulation. So, if we want to use this tool, we need to model actually the spray or combustion model. So it is necessary to develop the most useful models for new combustion model or new fuels. So the objective of this report is first is implementation and verification of purpose-free and the combustion model applies the single or bi-component fuels on the engine operating condition. And another is we developed a new analysis method for characterizing spray mixing process. And third is we developed a new method on determinations, the ignition delay or lift loss, and compared them with the Eastern Workshop reference method. So let's move to the first spray model. As we know, the digital spray model has been carried out by means the DDM method for more than 3 years. It has the procedure is the liquid phase we use the laberating dissipation, but for the gas phase we use the Eulerian dissipation. But most results have shown that in cylinder condition for IC engines are supercritical or near supercritical. So we found the boundary of the different phase like the liquid to gas not very clear. The definition is difficult or boundaries are not accurate enough with the existing models. So we need to in this report, in this research, we used a new spray modeling with the sigma Y model. The sigma Y spray modeling we use both phases to use the Eulerian discretization, and the liquid gas is considered as the total fluid with the variable distance and a single velocity field. And for the large scale feature, independent from process at a small scale under And we use the liquid mass fraction to describe the liquid mass. And for the atomization process, the model by the mean surface area of the liquid gas interface. As for the combustion model, we know the spree for the technically the diesel spree combustion is the whole non-promised diffused and is modified and compressed, and the time and spree scale is large range. And the most important there is the turbulence and chemical reaction. So, but we conclude all the issue. We can get the two very important issue. One is how to use the reaction mechanism. For detailed reaction mechanism, there is hundreds of species and thousands of the reactions. How to balance the accuracy and the cost. And then for the moment we converge the combustion model SAT use the well-mixed model. But this is right or not when used for this diesel spree combustion. And another question is the interaction between the turbulence and the chemistry. But we think the key issue is the decompressing and incorporating the two different parameters. So in this research, we use the UIPV combustion model. It is very similar with the last presentation. But for diesel spree, if the chemical reaction time is very small, and we can use a set of laminar flamelets to describe the diesel spree combustion. And any properties of the reactive flow can be replaced the mean mixture fraction and the variance mixture fraction and the scalar dispersion rate and the approximate value. And on the slide, there is a brief overview of this model's step. First, we can get the laminar manifold for solvers, the laminar flamelet, and then we use the PDF integrated to consider the turbulence and the chemical reaction, and then we got pre-calculate table for stores all the chemical information, and then coupled with the safety solver. This is our combination model setup. We use the 2D sector with the axis surface. The dome size is 100 mm and 25 mm. We have 505 axis cells in 3 axis direction, and with the expansive radius of 1.0. And we have 2 blocks in the ratio direction. One is for the injector nozzle. We have 10 cells, and the block 2 with the 100 cells with the expansion radius of 1.6. And the minimum size for the donor is 10 micrometer. And we have the 57,000 cells. And we use the OpenFOAM safety environment with the RANS combustion model. And this is the detail of we use the injector. The injector is from the Eulerian website. It's a very famous spree injector. And diameter is 19 milliseconds. And the key factor is 1.5 is the no cavitation. And the number is the nozzle is the only one, and the direction is the one axis. For the bottom and the right figure, we have the velocity in the nozzle. We have time. We have the velocity is changed with time for the injection of liquid. And this is the calculation metrics for this program. We simulations the dotting and PIF. We focused on the ignition delay, lake flow loss, and the flame structure. And for docking, we use the 5 mechanism with different species and reactions. But we need to check that the raw and the LLNL, these mechanisms include the Chongqing and another series without the Chongqing. For the PIP, we use the 2 different mechanisms. Mechanism A and mechanism B, because we use maximum A and not get very good results, and then we optimize and the mechanism B. The reference condition we use is the spring condition, which is as red for white. And then is the model validation. We first validation on the inner condition. In the life society, we compare the 3 axes of mixture fraction and velocity after start of injection 1.5 millisecond. And in the middle of 3 columns, we compare the distance, the downstream of the distance from the nozzle have 3 different to the nozzle. And this is the ratio direction. And at the same time, we compare with the vapor penetration and the liquid penetration. From the results, we can see the sigma Y 3 model accurately separates the 3 penetration and profile. Especially, we also compared with the DDM results. We found that our sigma Y model results better than HRT from the bottom and the right liquid loss. And then we applications this carbon models in the docking on the reacting condition. The first we compare the penetration and the vapor penetration and liquid penetration, and then we compare the 3 axes with the 5 different mechanisms. The velocity in the x-system. There is some difference at the end of injection, because maybe there's something different of the mechanism. And the axial velocity is slightly different in between the mechanism. Maybe and then the interaction, the result maybe is the interaction between the turbulence and the chemical reactions. And for the ignition delay, we compare with 2 different definitions. One is recommended from the ECM website, and one is from the other research work. And we check the yaw mechanism and the NAR mechanism. The yaw mechanism is the best result, but this yaw mechanism is very old one, and it's the last species and the reactions. And then for the as we know, as we introduction in the previous slide, we introduced our 3 combustion, our 3 model is all the Eulerian approach. So we use the logarithmic views to analyze the mixing fraction. We call the rest time of the fluid aging. It means that we release the massless particle from the downstream about 5 millimeters to the nozzle for each time, and then we check all the particles following the velocity and check the mixing. And we found the very right particle. It means that very earlier into this convection experiment. And we select the one point of the ignition as the ignition for yaw and NARA. We found the ignition location with the suitable temperature and the equivalence ratios. And then the ignition not always the earliest injected, and the injection equipment ratio is similar, but the location is very different. For your, it has the range maybe wider. For Nara, the range is narrow. And then the mixing and the chemical reaction determines the ignition location. For your, we can check for your mechanism. The reaction maybe is around has some distance to the spring axis. It's moved to the axial direction. For your, for Nara, the ignition location is around near the spring axis. And that is the lift of last. As the Eastern Web Software recommends, the lift last is the first axial location of favoring a range OH mass fraction reaching 2% of its maximum in the domain. Some research always use 15% instead of 2%, and others research also use temperatures from the ambient temperature plus the 400 to go to the lift last. But actually, in the experiments, the Eastern didn't use this method. They use the shortest distance from the orifice free, actually 50% maximum OH star. So in this research, we always use the project the OH star reach 5% of the stable value. It means that we copied our simulation domain to the 3D and then projected to the and then projection is the vertical spring axial direction. And then we compared the 5 different mechanisms with the 4 different lift of last definition. We checked we can check the mechanism of yaw and Nara is constant with the experiment, and then the UFPB models are more accurate than well mixed. It means that it's better than the converged SAT model. And this the reconstruction the OG star is reliable. And this is the control profile of the lift of the steady. We can check the OH and OX in the near storm ratio. OH exists in the downstream of spring. OH star exists upstream of spring and as the lift of last. OH star has a short life in near stormetry, with the high heat service rating. It means that the OH star means exactly the state of the OH, and OH is the ground state of the OH. So there is the OH star, twin to OH, there is the huge heat release rate. And in the right figure, we constant project the OH star with the experiment results. We can check in our this method. The result is very constant with the experiment. And then we check okay, no problem. We check the application of PRC CM model. We use the new ignition delay. This ignition delay is from the numerical salary. This method is very constant with the experiment loss. The ignition delay is made from the Shang numerical loss. And this is 2 different PRC mechanisms and 2 different ignition delay results. We can test. We can check. We can check all this. The methods. The ignition delay is constant with the traditional definition. And this is the 5 different PRC results compared to numerical sharing and the experiment results. We can the numerical sharing method can actually capture the direct profile. And we also compare the ignition of the fluid engine. Its results are very similar with Chongqing. And another, we also compare the lift balance for the PRC. We check in the middle of the column. We we find the with the OH star is more better than use the OH. And the right star is the projections the OH star we compared with the results. Okay, this works the results.